So I promised you last time when we talked about the inverse of the exponential, what we did to find that inverse, if you look back on your notes, we just put that note sheet away. But if you look back on your notes, what we did is we had graphed 2 to the x power, okay, because we know how to work with the exponential. And then we had manually gone in and flip-flopped all the x and y values. And we came up with the graph of the inverse, which is called the logarithm, we found out. And so here on my work, this is what it looked like. We graphed the 2 to the x power, and then we flip-flopped all the x and y values, and we came up with this. But that was before we knew that the inverse of the exponential was called the logarithm, before we knew anything about it, that we had already graphed it. So now I want to be able to skip this step of graphing the exponential. I want to go directly to graphing the logarithm or the inverse function. And that's what we're going to talk about here at the beginning of section 6.4. So the first thing we're going to do together is example 1, and we're going to graph from scratch the log base 2 of x. We're going to come up with this same exact graph that we saw last time, but now I'm just going to show you how you graph a logarithm. Okay, how do you think through this thing that's brand new and kind of different? So I'm going to start the same place that we started when we did graph the exponential, is I'm going to create an XY table. And I liken this to way back when we first started graphing our basic functions, and we graphed the square root and we graphed the cube root. And my advice to you back then was pick values that, when you're graphing the cube root, pick values that have a good cube root. So we picked 8 and we picked 1 and -1 and -8 because we could take the cube root of those easily. So my advice is the same right here. When I'm graphing the log base 2 of x, what we're going to do is we're going to pick values that have a good log base 2. And since the logarithm is a power, we're going to pick things that are powers of 2. So for instance, I'm going to pick 8, and I'm going to pick 4, and 2, and 1.5. Anything that is a power of 2. That's the secret to graphing a logarithm, is you pick things, you pick your x values that are powers of the base. Because you avoid then a whole lot of hardship and a whole lot of calculator work. I pick things that are powers of the base. So I don't think I have enough room here. So let's just, for the first couple, I'm going to write this out. So when I put an 8 in here, I have the log base 2 of 8. Now remember, the logarithm is a power. What this is saying is 2 to what power, because the logarithm is a power, 2 to what power is 8? And you would answer 3. 2 to the third power is 8. So the trick to using logarithms is to remember they are a power. You've got to think in terms of the exponent. So for the next one, log base 2 of 4. Well, same question. 2 to what power is 4? 2. 2 to the second power is 4, and on down the line. So the log base 2, I'll just keep writing it out because it's making me happy. Log base 2 of 2. Well, 2 to what power is 2? 2 to the first power, okay, 2 to the 1. Log base 2 of 1. 2 to what power is 1? Well, we saw this in our properties of logarithms. The logarithm of any base of 1 is equal to 0. Yeah, the 0 power, perfect. And then last but not least, the log base 2 of 1/2 is equal to, well, 2 to what power is 1/2? What do I have to do to the power to shift the base down to the bottom to make it 1/2? It's negative, so now it's -1. So the key, again, just to repeat myself, is you pick x values that are powers of the base. That is the key to making this as easy as possible. So now I'm going to graph these points. The x value is 8. The y value is 3. The x value is 4. The y value is 2. The x value is 2. The y value is 1. The x value is 1. The y value is 0. Then the x value is 1/2. the y value is -1. This shouldn't be a surprise. This should be the exact same graph that we did last time when we just flipped the points of the exponential, and it is. And I think we answered these same two questions back when we talked about the graph of the inverse of the exponential, but we're going to answer them again. Here's the tricky one. What's the domain of this function? Where do the x values start on this logarithmic function? At 0. And where do the x values go to? How far to the right? Infinity. At the 0, remember, that is an asymptote, so we're going to put a parenthesis, not a bracket. And if you need to, just do your dotted line right here. It's hard to see because I'm using black on the black y-axis, so I think you can see it a little bit there. Probably should pick a more vibrant color there. What's the range? Well, how far down does this go? -infinity. How far up does it go? There you go. Perfect. Well, if you would do the same thing for me for exercise 1, I just changed the base so that you would get the pleasure of working through it. To address the question that was asked earlier when we were dealing with the exponential, how many points do I need to use? I just pick as many x values as are going to fit on my graph, to be quite honest with you. So following my advice that we're going to pick powers of the base as my x values, what are some good powers of the base that I should pick as my x values? 9's a great one. 3, 1, sure, a third. You can pick a 9th if you're a glutton for punishment. That's great too, but that's getting pretty small, and I don't know how it's going to show up. So 9, when I plug that in, I don't have room, so I'm just going to write it down here. If I have the log base 3 of 9, well, 3 to what power is 9? Perfect. And then I have log base 3 of 3. 3 to what power is 3? I'm hoping you would say 1. Log base 3 of 1. Well, again, The log any base of 1 is going to be 0. Anything to the 0 power is what gives you 1. And then last but not least, the log base 3 of a third, that's going to give me -1. These are the powers of 3 that result in these values. So now when I go over 9, I go up 2. When I go over 3, I go up 1. Over 1, up 0, and then a third -1. So the shape of this graph is similar to the previous one, but you notice it's not increasing quite as fast. Which, by the way, if your math destiny is taking you there, you're going to get to calculus and you're going to get into all the how fast things are increasing and being able to predict that. And it's so much fun. You're going to have a great time. And hopefully you'll remember me fondly when you get to the calculus of the logarithmic graphs. What is the domain of f of x? Well, again, that doesn't change. That's 0 to infinity. What is the range? The y values are -infinity to infinity. So that looks very similar. I've got one more exercise just because I know getting used to thinking in terms of logarithms is sometimes difficult. So I don't know what I typed here. Exercise E2. Great. I'm going to cross out the E. So we'll fix that next semester. It doesn't really help you today. So if you could graph the log base 5 of x, please. Once again, to graph this, I'm going to pick as my x values the power of the base, which is 5. I'm really kind of limited by the size of my graph, so I'm just going to pick 5 and 1 and 1/5. That's really all I've got that's going to fit on this grid. So the log base 5 of 5 is going to give me 1. The log base 5 of 1 gives me 0. And then the log base 5 of a fifth gives me -1. There's my values. So I'm going to put some points. So I've got 5 and 1. I've got 1 and 0 and a fifth and -1. And so again, you can see it's the same basic shape as the previous two, but this one's increasing even more slowly because the base of the logarithm is bigger. So that's the first objective for this section, is being able to graph logarithmic functions. Before we move on to objective 2, is there a question about that? Well, we'll come back to the graphs in just a minute. That'll be our final objective for this section. So the second thing is, well, okay, what if I don't want you to graph the logarithm? I just want to know what its domain is. So the next few problems, we're going to find the domain of these logarithms. So before I do my example 2, I'm just going to remind you, I'm just going to carry over something we had on the previous page. If I have log base, it doesn't matter. All the examples I gave you are base 2, but I'm just going to say any base because it doesn't matter. The log base, any base of x. Well, from the graphs, we've seen that the domain are my x values have to be bigger than what? Not bigger than 1, 0. Yes. So the domain is my x values are bigger than 0. Remember, the y-axis is our vertical asymptote. So all of my x values that I plug in have to be bigger than 0. So that's true of any logarithm, no matter what the base is. So that's why I used any base a. And so that applies up here. So this is very similar, again, to when we were finding domains of square root functions. I could only take the square root of things that were, in that case, bigger than or equal to 0. And so we scooped out what was under the radical, and we said, okay, that has to be bigger than or equal to 0. So the same thing is true here. What I'm going to do for this logarithm is I'm going to say, okay, this thing right here that I'm taking the logarithm of, in this case, x minus 1, it has to be bigger than 0. Now I picked a nice simple example for myself because I'm just coming off the weekend and I didn't want to tax my brain too much. So I'm going to add 1 to both sides, and I get that x then has to be bigger than 1. I'm going to write that in interval notation. And so if my values are all bigger than 1, that means that 1 is the lower end of the interval. Everything else is bigger, meaning it goes to infinity. And I'm going to put a parenthesis at both sides. Because remember, this is a vertical asymptote at the lower end of the interval. So you're never going to be equal to that value. You cannot take the logarithm of 0. So with that knowledge, if you would please do exercise 3. So what's the inequality that you set up in order to find the domain of log base 2 of 5 minus 2x? Okay, whatever you're taking the log of, in this case 5 minus 2x, has to be bigger than 0. Because we cannot take the logarithm of something negative, nor can we take the logarithm of 0 itself. Has to be a positive value. So that means that the 5 minus 2x has to be positive. So I will solve this now. I'll subtract the 5 from both sides and get negative 2x is bigger than negative 5. Divide both sides by negative 2. This is just a little reflection on solving inequalities from way back at the beginning of our class time together. And so that means I have to flip the inequality sign, and it becomes x less than 5 over 2. So any x value less than 5 over 2 will produce a positive net result that I can take the logarithm of. So since all of my values are less than 5 over 2, that means 5 over 2 is the upper bound of my interval, and everything is going to be below that. So negative infinity, and I put parentheses around both sides. Now I will forewarn you, the next one is a difficult problem, okay? I did not want to just make you regret coming to class today with easy problems. So I'm going to give you a little extra time. This time we've got the function log base 2 of the absolute value of 3x minus 7. So it's an absolute value problem. Blast from the past. Give it a try, please. I didn't pick a great problem. I messed up. That's okay. We'll learn from this. I'll be a better instructor someday. So we've got the log base 2 of absolute value of 3x minus 7. So again, the key here, the thing I'm hoping you learned, is that whatever I'm taking the logarithm of has to be, so the absolute value of 3x minus 7 has to be bigger than 0. So this is where I thought the problem might be a little different, but I wasn't thinking ahead. The absolute value is always going to be positive, right? In fact, there's only one value that I have to exclude, because the absolute value of 3x minus 7 is always going to be bigger than or equal to 0, because absolute value always gives you a positive outcome. So the only value to exclude is when 3x minus 7 equals 0, because we can't take the logarithm of 0. So that happens when 3x equals 7. When I divide, x is equal to 7/3. Every other input that I put into this absolute value is going to give me a positive result. The only thing I have to exclude is 7/3, because that gives me a value of 0, and we can't take the absolute value of 0. So what's the domain of this? Well, the domain is negative infinity to 7/3, parenthesis, union 7/3 to infinity. It's not the problem I thought it was going to be, but it still gave us something to talk about. Our absolute value will never be negative, so we don't have to worry about any negative values occurring. The only thing that we worry about is the input that gives me 0, because we cannot take the logarithm of 0. Final thing for us today. So first objective from this section was graphing logarithmic functions. Second objective was the domain and understanding that what you put into a logarithm has to be bigger than a 0. The last thing is what we've done with every function that we've graphed, whether it was exponential or our basic functions or anything else, is we've talked about the transformations of them. So this first one, this is my example. I'm going to do this, then I've got a couple for you to do. We're going to graph f of x equal to the log base 2 of x plus 2. Well, if we flip back to the front page, we've already graphed the log base 2 of x. And I'm just going to throw down in pencil those points on this graph. The points were at 8, gave me an output of 3. At 4, gave me an output of 2. At 2, gave me an output of 1, 1, 0, and a half, negative 1. And you might be saying, Mr. Perkins, where'd you get those? Those are just the points from our front page. That's it. So this is log base 2 of x right there. Here's where you come in to help me. Uh-oh, what's going on here? Okay, we're back. Let me just make sure everything is still set up because of whatever just happened. Okay, right microphone, camera looks good. Okay. So before the power failure there, I've graphed log base 2 of x. This is where you're going to help me. Since I've got an x plus 2 here, what does that do to my basic function? Moves the whole thing left 2 units. Same thing we've been doing the entire semester. I'm just going to take each of those points on the basic function, and I'm going to move each of them left 2. So instead of being 8, 3, I'm going to move it back 2, so it's 6, 3. Instead of being 4, 2, I'm going to move it left 2, so it's 2, 2. Instead of being 2, 1, I'm going to move it left 2, so it's 0, 1. Instead of being 1, 0, when I move it left 2, it's negative 1. And then instead of being a half negative 1, I move it back, so 1, 2, it's going to be negative 1.5. My vertical asymptote also moves back, and just so I don't forget it's there, I'm going to put my vertical asymptote here nice and thin so that I don't crash into it right here at negative 2. And here is my graph in purple of the natural log, or excuse me, the log base 2 of x plus 2. So the example I have for you, or the first exercise I have for you, is also based on the log base 2 graph. So if you want to pencil that in or do that lighter, put your basic graph and then answer the question, what does that minus 3, the way it's written, notice there's no parentheses there, that makes a difference. What is that minus 3 doing to the graph? And I'll give you a few minutes to think about that. Once again, in pencil, I have drawn the log base 2 of x graph. So log base 2 of 8 is 3, log base 2 of 4 is 2, log base 2 of 2 is 1, log base 2 of 1 is 0, and log base 2 of a half is negative 1. Those are the same points we've used. Now, this minus 3, there's no parentheses. So that minus 3 is telling me to do what with the graph? It's going down, yes. So those parentheses, the reason I have these two examples side by side is those parentheses are telling you something different. Okay, when the parentheses are there, that's grouping the number with the x. So that is a horizontal translation. When there is no parentheses, that's being done to the original function. And so it's a vertical translation. And so I'm going to move everything down 3 units. So 8, 3 moves down 3. This one moves down 3, down 3, down 3, and then down 3. The vertical asymptote is not going to change because we've not moved the graph left or right at all. So that's going to stay the same. And here is my new graph. Lovely. Questions, comments, concerns? All right, last page. So exercise 6, I'm using the log base 3 graph. So if you could please do the translation of the log base 3 graph described in exercise 6. My log base 3 graph has these basic points right here. At 9, log base 3 of 9 was 2. Log base 3 of 3 was 1. Log base 3 of 1 is 0. Log base 3 of a third is -1. Those are my points. So two things are happening to this graph when I translate it. What does the x minus 3, what does that tell me about the graph? Okay, we're going to go right 3. And then the plus 1 tells me to go up 1. Right 3, up 1. So this first point, well, I got to do a little guesstimating. 1, 2, 3, up 1. It's going to be right about here. This one, 1, 2, 3, up 1. 1, 2, 3, up 1. And then finally, 1, 2, 3, up 1. There's my points. I've moved the graph right 3, so that means my vertical asymptote also is going to go right 3. So I'll put it right here so I know that I shouldn't, my domain is not going to be all the x values. And here is my graph now. Beautiful. Last problem for the day is again based on the log base 3 graph. So I'll give you a minute and a half or so to finish this out. This time there's a negative in front of the log base 3 graph. All right, for this final example, again, I've got the same basic points. I've replotted them on this grid. If you need to do that, great. If you don't, great. What is this negative out in front of the logarithmic function going to do? It makes all the y's negative. Perfect. Well said. And that happens because it's out front. And before I graph that, that just leads me to this question. What if I had said this, the log base 3 of negative x? All the x's would be negative. Yes, the position of that negative makes a difference. Okay, so just be careful. This one, I'm making all the y's negative, though, the problem that we have. So this will be, instead of a positive 2, it's going to be a negative 2. Instead of a positive 1, it'll be a negative 1. 0 stays 0. Instead of a negative 1, it becomes a positive 1. So we get this reflection about the x-axis because we have made all of the y values negative. Notice nothing happens to the asymptote because we've not moved the graph left or right at all. And so this is negative log base 3